Video lab report investigating 2D inelastic collisions, group 6A. My name is Jalisa McQueen.
Jaclyn,
and Anna Khalil.
Inelastic collisions are collisions where the object's kinetic energy is converted to other forms of energy like internal energy. The majority of collisions that happen are inelastic. For example, when two objects collide, we can usually hear them. This shows how some of the kinetic energy is converted into sound energy. An elastic collision would describe a collision in which all of the kinetic energy and momentum is conserved.
Our question asks, how does changing the velocity affect the fraction of kinetic energy lost? If the ball is thrown down with a greater velocity, that will return a greater loss in kinetic energy. The velocity of the ball decreases with each bounce, so when the ball comes in contact with the ground, some kinetic energy is transferred into the ground, which makes the ball's speed slow down after the collision. A lower final velocity implies a loss of kinetic energy, which is why the ball is unable to bounce as high as it did the first time. This led us to hypothesize that the greater the initial velocity, the greater the fraction of kinetic energy lost.
In our experiment, we dropped a ball from a height of 1 meter and 54 centimeters for 3 trials. With each trial, we slightly increased the speed with which we threw the ball in order to test how the change in velocity would affect the fraction of kinetic energy lost. Our system schema shows the ball having a contact and gravity interaction with the Earth. The first image shows the ball after the initial release moving in a downward direction. The image below shows the collision of the ball with the Earth, and the image on the right shows the ball after the first bounce.
During trial 1, we threw the ball at the lowest velocity. We expect that the fraction of kinetic energy lost between the two bounces to be the lowest among the 3 trials. The ball started at a height of 1.2 meters, and after the first bounce, it only went back up 0.9 meters. The ball had an initial velocity of 5.04 meters per second before the first bounce and a velocity of 4.55 meters per second before the second bounce, making the overall change in velocity 0.49 meters per second.
For trial 2, we threw the ball with a medium velocity. We expect the fraction of kinetic energy lost to be slightly higher than the previous trial because trial 2 has a greater change in velocity between the two bounces. The ball started at a height of 1.2 meters, and after the first bounce, the ball reaches a height of about 1 meter. With an initial velocity of 7.14 meters per second and a final velocity of 5.02 meters per second, there is an overall change in velocity of 2.12 meters per second.
For trial 3, we threw the ball with the highest velocity. We expect the fraction of kinetic energy lost to be higher than the previous trial because trial 3 has a greater change in velocity between the two bounces than both trial 1 and trial 2. The ball started at a height of 1.2 meters, and after the first bounce, the ball reaches a height of about 1.19 meters. With an initial velocity of 6.67 meters per second and a final velocity of 4.17 meters per second, there is an overall change in velocity of 2.5 meters per second.
To ensure our experiment was a 2D collision and not a 1D collision, we threw the ball down at an angle so there was a change in height in the y direction and also horizontal distance from the origin in the x direction. The changes in velocity are relevant to our research question because we are trying to see the relationship between velocity and kinetic energy loss. In order to understand these relationships, we need to find the change in velocities, compare them, and see any trends between the trials. It should be noted that throwing the ball from inconsistent heights, inconsistent angles of depression, which is the angle in which the ball was thrown downward, could cause flaws and minor inconsistencies in our data.
The formulas used are based off of the equation for kinetic energy, which is 1/2 mv squared. To find the percent of kinetic energy lost, we need to take the initial kinetic energy minus the final kinetic energy, all divided by the initial kinetic energy. However, because the mass of the ball is constant, we can simply factor out the 1/2 times mass out of the equation, which leaves us with an initial velocity squared minus final velocity squared divided by the initial velocity squared. We then multiply the resulting decimal by 100 to give us our percentage. Using this method, we found the percentages of kinetic energy lost in trials 1, 2, and 3 to be 18.5%, 50.6%, and 60.9%. The way this works is that a greater change in velocity will produce a larger value in the numerator, resulting in an overall greater loss of kinetic energy.
Observations from our experiment do match the evidence presented in physics. Our change in velocities are greater with each trial, meaning there is a greater amount of kinetic energy to be lost. Therefore, we can conclude that a greater change in velocity means a greater loss of kinetic energy.